Good morning. This is Monday, the 4th of October. It's going to be a beautiful week. I'm just saying this for those of you that are watching the video at some point in time. It's really what Colorado would advertise as being the ideal fall weather. Lows in around 45, mid-temperatures around 75. Could we ask for anything nicer?
Yeah, I agree. It's good.
It's really nice. I was out, I do a lot of walking, and I was up in Monument because that's where my mother-in-law lives, and mostly fir trees out there, but some bright deciduous trees with bright yellow leaves, not aspen, but so we know it's fall. And so I've got stuff in my yard that's turning bright red as it normally does in the fall, so all that stuff's happening too. So to focus on what we're going to jump back in and can pick up from where we left off with the matched filter. I'm going to review a couple of the core steps and where we are with that. But before I do that, I'm going to point out that over the weekend, especially yesterday afternoon, I spent some time doing two things. I updated Chapter 5 notes. I eliminated a bunch of source code stuff that I had in there from MATLAB. I haven't pulled the MATLAB out in the examples, but I said all the source code listing is taking up a lot of space. I improved a few things. Every time I read it, I see more things I could tweak on it, grammar-wise, etc. But the other thing I did is I went to the Jupyter Notebook that we were looking at last time, and we'll be looking at again. It's the one called Data Transmission in Noise. And I've pretty much polished that up all the way to the end. I have everything working in there now to my liking. I did some more remapping of code that was originally only in MATLAB, all into Python now. Now I have to think in the future, do I want to add it to scikit DSP-COM dot digital comms module. I went off in different directions with that module, but the material in this chapter has just sort of been hanging out there, and I'm not sure if I want to do it. Maybe you'll give me an inspiration that I should push it in there. It's certainly at my will because I'm the author of the code, but it's in this notebook, and that's probably the most important thing to know for right now, that we can get access to it. So I'm going to go back over here, though, and just get back into where we were. We came through basic rectangular pulse binary waveform. It's actually a non-return to zero waveform that we were looking at, and it was called binary antipodal on top of that. Binary antipodal just meaning it took on two levels, plus A, minus A, and the pulse shapes were rectangular. We're going to start talking more about all of the other details that do matter, because pulse shape controls spectrum, pulse shape controls synchronization aspects. We won't get into synchronization until the next chapter, and then pulse shape is also controls performance on top of that, because signals generally don't go through a channel without suffering some impairment, like band limiting, let's say, and you're going to be experiencing that soon in a simulation model. But the first step was to establish working with arbitrary signal shapes, and that can be amplitude, pulse shaping, time duration, and so on. It can be anything, because the way we set this up, we said we're going to send two different pulses of finite duration. Now, we're saying they're constrained right now to be what would be called the full response type of signal. The signals lie within an interval of 0 to t seconds, where t is the bit period, but they don't necessarily land on top of each other. So when you signal with them, they can be at different points within the signaling interval, and they can have different amplitudes and, like I said, pulse shapes as well. And there's some homework problems that revolve around that and allow you to sort of jump in and see how this theory works out. We will be spending more time on some classical types, though, that fit this model, and that would be basic amplitude shift keying, binary amplitude shift keying. We'll get into M-ary amplitude shift keying in a little later in this chapter, phase shift keying, which will be the basic binary form, and binary frequency shift keying. All of these, eventually are M-ary schemes when we get rolling into the next chapter. The ASK is the first one to take that plunge, and that's later in this chapter. So these were just the way the signal shapes were defined, are defined for these three types in their binary form. But we're not going to jump back over to this for a little bit. Instead, we went off and we looked at how do we design the receiver. So a generic receiver was posed as being consisting of two filters that had an impulse response H1 and an impulse response H2, and you would form the difference in an attempt to get a decision statistic that could decide which pulse shape was sent. So under sending pulse shape of type 1 or binary 1, it would be S1 plus noise, and pulse shape 2 plus noise when you're sending a 0. And one of the things I was looking at when I was reviewing this yesterday or this morning or sometime in between, I don't want you to get confused into thinking that I use a filter H1 when I know I'm going to receive an S1, and I use a filter H2 when I know I'm going to receive an S2. There's something fundamentally very wrong with that, and what is that?
You don't know what you're receiving.
Exactly. But you could get yourself confused with that. I mean, I could just imagine somebody, a younger student, saying, yeah, I'll do that. That'll work perfectly. Well, it won't work perfectly because we want to send random bits, and that's what information theory would tell us. We want that randomness because that's what contains information for us. So in this case, the structure is just saying we have a filter that's kind of going to do something more significant in pulling out information from S2, and something that's more in H1 is more significant in pulling out the S1 when it is sent. And if you want something to think about, though, fundamentally, and this is not strictly required, but you could think of S1 and S2 being orthogonal, right? Orthogonal in a signal sense. And then the filter H2 pulls out only the S2 signal, and meanwhile the output of filter H1 is nothing when S2 is being sent, because these filters have this orthogonality property. And the easiest modulation scheme to think of for that, I think, is frequency shift keying, where you think of,
Two bandpass filters.
yeah, exactly, two bandpass filters. So that's kind of where that comes into play. But because this is very generic, the way the book develops this, they just said, well, we have a certain amount of noise, and that noise is going to be the composite frequency response, which we're going to define as just the difference between the two. And all of this is based on the fact that the front end there is linear. So we have a signal arriving. It just so happens in this form to be split out like that, and then it goes into the differencing, and that's all linear. So V of t is just a linear processed version of the input, which is called y of t. So we went through that. We looked at, under Gaussian statistics, that we would have something like this going on. Just, again, a very generic result saying we get a response when we send S1, we'll get a response with a PDF on the left side, and then when we send an S2, we'll get a PDF that's shifted off to the right side. It could be totally different than that. It could be flipped over. They could both be on the positive side, both be on the negative side, but it's some means of detecting that there's two different types of waveforms being received, and we can put a threshold in between and then get some sort of probability of error associated with making the wrong choice. So we did that and said that if it is truly Gaussian, which in the linear filtering model, we'll have Gaussian statistics, and then we'll have the Q function, and we could go through, we're just saying right now under equally likely cases, the threshold will be at the midpoint between these two conditional values, and these are also called conditional means as we go through the statistics. And then that would be the Q function. So that is nice to know, nice result, extends from everything we've been doing, but it still doesn't do anything with how to choose H of t, the equivalent impulse response of the receiver front end. So that was the discussion we did last time. I'm not going to go through the Schwartz inequality math unless you have questions on it, but I'm just sort of going to wheel our way down, and we came up with this result that says that the optimum, and that's what the 0 is for, the optimum filter is the time-reversed impulse response shifted for causality reasons of the difference between S2 and S1. And again, the signs could be flipped around. It's just the way it was defined here. So the important thing is that it's the time-reversed impulse response of the pulse shapes that comes into play here. And again, going back to what I was saying a moment ago, if the signal passes through a filter like this, and S1 is orthogonal to S2, so an S1 goes through and gets convolved with this H naught impulse response, the second term is going to give some large output because it resonates with it, whereas S2 is going to get ignored if S1 and S2 are orthogonal pulse shapes, and then vice versa. So that all works out nicely. So the first example that the book uses is just saying it's the rectangular pulse shape, which in this case, this is just the rectangle using the capital pi function and then shifting it by t over 2 so that it truly is a causal pulse shape. So let's see if I can draw that. See if my pen will start working. It's not wanting to work. It's wanting to disconnect. So it's causal because it starts at 0. So now if we go down here and design our matched filter for that pulse shape and go through the operation of convolving it, like we would do with the linear filter in the front end, or just showing the convolution on the left-hand side, sliding it across. T naught is an arbitrary offset just to ensure causality. And then we get the output, which is the triangle shape. And in this case, we would set T naught equal to, see if this thing will come back to me. T naught equal to capital T, so that indeed we can sample at capital T. And in reality, this is very much like the integrated jump receiver that we were looking at in the very beginning, because we're just integrating a rectangular pulse, and that's what's going on right in here. Then make the decision right there at the top, and that should give us our peak signal-to-noise ratio, which should give the minimum probability of error. The only thing that maybe seems funky about this is, what about S2? There's no S1 or S2 in this case, but if it helps, you can just simply say we're going to send a pulse when we want to send a 1, and we're going to send nothing when we want to send a 0. That would be a very simple form of pulse amplitude modulation, or in optical communications, it would be called on-off keying. So we're just looking for the presence of something, or not the presence of something. And this really is, I think, kind of the foundation of where the matched filter theory came into being, because it was looking in radar applications for a target, and you were going to send a burst of RF out into space, and if there's a plane flying at you, you'd get a reflection off of it. So that burst would come back, and then you would filter that signal in the receiver with this matched filter, and then you would time it to get, or look for the maximum deflection and sample that, and that would be your, target present, target not present type of scenario. So that was really an on-off keying situation. I believe I'm not a radar expert by any means, but does that sound reasonable from a modeling standpoint? So then we get into, okay, now we know what this optimum is, and we can come up with it. Then some other definitions come into play, namely that this zeta max is that ratio that we defined way back over here. Zeta was, let's see, where did it show up? Right in here. Or I think, yeah, zeta squared, or zeta is the deflection at the output of the filter divided by sigma naught for the particular noise variance that we get in going through this filter, G naught. So that's our figure of merit, which is a signal to noise ratio type quantity. But now adding some more thoughts onto that, we can go through Parseval's theorem for Fourier transforms, and we have this definition for zeta squared max, which comes out from the matched filter theory involving the pulse function, time reverse pulse function spectrum G of F. And that's the difference between the two pulse functions. And then this is where Parseval's theorem gets applied. It just says we can take that calculation, which if you think back from linear systems theory, that's an energy calculation, right? The first integral there that I have the red brace under is the energy in those difference of those two spectra, the spectra of S2, its pulse, and the spectra of S1's pulse, magnitude squared. That should give you energy in joules, and Parseval's theorem says that we can also get that by integrating the pulse is in the time domain, magnitude squared, and those are equivalent through Parseval's theorem. So when you expand out that quantity, S2 of t minus S1 of t, you get three terms, and those are the three terms right here, with them having a special definition. The first one, this one right here, is going to be the energy in pulse 2. That's going to be the energy in pulse 1. And then the term at the end, the product, is going to be the correlation between the two signals. And that can be defined through a normalization. It can be defined as related to a correlation coefficient in the time domain. I mean, we had correlation coefficient for random variables, right? This is just a correlation coefficient for time domain signals now. So we can say that that correlation is going to be can be normalized to be a correlation coefficient, so it ranges between -1 and 1, as long as we divide by the geometric mean of the energies. Isn't that what that is? Square root of E1 times E2, geometric mean.
Is it basically saying, right, if I understand, it's easier to decode signals if S1 and S2 are orthogonal? Because then that term will be 0.
It is, but you asked a really perfect question, because now we're going to come along and say, wait a minute, that looks nice, but look at what happens when we make this substitution in here. So we have this. If we dwell on this, is it best if that is equal to 0? Since zeta squared is like a distance between S1 and S2 in an abstract vector space, okay? We do abstract vector spaces more in the next chapter, but because we have E1 plus E2, which can't change, I mean, they each have a respective energy. So because we have a minus sign in there, what does that tell us? We should be able to do better if we don't make them orthogonal, because if we can make them be negatively correlated, then we'll have more distance between them. And that's exactly what binary antipodal does, is it puts them plus and minus, or I guess I get from your point of view, plus and minus, so their distance is further, whereas orthogonal would be plus and 0. So it turns out there's a 3 dB performance penalty. This just puts it back into the Q function using that correlation coefficient, and then it further defines E as the average received energy per bit, assuming that you might choose to use different energy levels for the two pulse shapes. And then the statement that it would be advantageous if we could make the correlation coefficient equal -1, so we could obtain the maximum Q function argument and the minimum error probability. It's very cool. I mean, you guys are young, I'm old, but there's people way older than me that, some of them are deceased now, I think probably many of them are, that came up with some really nice signal designs that said, let's go with antipodal, let's take it to Emery by, they came up with a bunch of basic signal theory ideas for digital modulation that said this is the optimum signaling set to use. But of course the math is one thing, so when I teach this, I tend to think a lot about the math, and some of you that are more math inclined think the math is great, I love it to death, I'll just do it this way. But then if you talk to the engineering team that's doing the implementation, they're going to say, you've created something that's beautiful mathematically, but I can't build this. So there always has to be a balance between what looks good on paper and what you can actually build. So another way that the book...
What did you define Z as?
Well, we defined Z a long time ago, but I can flip back to it. That was EB over N naught. That's what that was. I should go back. I did add this to the notes since I reposted them. I added this comment, recall the integrate and dump receiver.
Okay, I didn't realize you were using the same variable name.
Yeah, I am. Trying to be consistent with the book for sure, but yeah, Z was the decision statistic that comes out of all this. So the author also defines capital R as another way of looking at the correlation coefficient, and this one involves the energies, so it's not a dimensionless quantity. Well, I guess it is. No, it's not dimensionless, right? Or it is? Yeah, it is.
I think it is dimensional.
Yeah, it is, because we have square root of E1 times E2, so that is units of energy, and the denominator is energy, and rho is dimensionless. So it's still, I'm not exactly sure why he does this, but I don't use it in my studying of modulation theory, but he has this notation in the book. So when E1 equals E2, then R12 equals -1 in the terminology of antipodal. So we get Q of square root of 2Z, which is what we had before for the integrate and dump receiver. If we were to set this R12 equal to 0, then we'd have orthogonal signals, and I just went ahead and plotted this out so you can see that the error probability curve pushes out by 3 dB approximately in the neighborhood of 10 to the -5, 10 to the -6. So definitely not as good a performance as the antipodal would be. So now before we start studying these specific schemes, we're going to also go through this thing that I pointed out at the end of class last week, correlator implementation. So we know now that if we have a rectangular pulse, or REC as some people denote it, integrate and dump and match filter receivers give the same performance, because the integrator and the integrate and dump receiver is like the match filter. It's just integrating up until t seconds, and then you make your decision. So that's like the leading edge of the integrating operation of the convolution in the match filter. So now what about, and that's like a correlator operation too, so let's just see how that unfolds. This is the match filter. Signal comes along. We have time reversed and shifted for causality impulse response, make a decision. The correlator view of it is down below, and it just says we're going to multiply times that signal in the receiver. What's inside the blue box is what goes on in the receiver. So we're going to take the received signal multiplied by S of t and then integrate. So to see that they're equivalent, we can look at what the convolution integral looks like right here. And then, of course, we're going to sample that at cap t. So when we make that substitution of capital T and change variables around, and I haven't gone through all the steps of how I change the variables, but it does reduce down to an integral of the two shapes, and then you just integrate from 0 to t seconds. For the case of the correlator, you're going to come in and multiply by the reference waveform, or the reference waveform multiplies the received signal y of t, and then you integrate up to t seconds, and that ends up being equivalent. In a lot of different things that I work on, I tend to like the correlator view better. And in some of the structures we're going to be looking at when we go through M-array schemes and signal space viewpoint in the next chapter, that correlator tends to be the better way of looking at it. I mean, mathematically, it's considerably more satisfying to say we're just going to correlate our received signal with all the different types of signals we expect in our set or collection of waveforms that could be coming at us, and then we're going to take the output of the correlators, like a bank of M correlators, and then we're going to have the max operator. We're going to take the one that's the maximum and say that was the one that must have been sent. And that makes sense, doesn't it? I think machine learning algorithms do this exact same thing. They will correlate with a template. I think of it as a template. So in this view right here, the S of t is like a template. And when I've worked on some advanced receivers, it's exactly what it has to be. In this space-time coding project I've worked on, I had these templates that were very complicated, complex baseband waveforms over a certain interval, decision depth or memory depth, and those were required to be stored in a lookup table, and then they would be played against the received signal, and then the correlator output would be used. The various correlator outputs would be used to extract decision statistics, which in the case of that receiver would go into a maximum likelihood sequence estimator, which is also equivalent to a Viterbi algorithm, and then use that together to take all those statistics and then over time be able to trace back and say, yes, this is what was sent, that type of thing. So for binary signaling, if we were to go with a correlator, this is, this will get extended to the M-array case, but for the binary case, it could look like this. We're going to multiply by S1 and S2, the received signal, correlate, and choose the largest. Like I said, I really like this a lot, the way this works out, because if you think of the correlation operation as being an inner product with a reference or template waveform, and then the signal that's coming in is now going to get projected onto that reference waveform's space, if a signal is an abstract vector space, but it gets projected onto its plane or whatever, in an abstract sense, it's that inner product, and then the lower correlator is the inner product of the received signal with the other template waveform, and then the one that gets the largest correlation is the one that is most likely to have been sent. And of course, the threshold, that's the thing that's being ignored here, is that the threshold, it says choose the largest, but actually what's missing that we'll have later is there would be a scale factor in the output of those correlators to account for the fact that if one is not as likely as the other, you would bias things a little bit one way or the other, right? We talked about that last time, I think, too. If the one is sent far more frequently than the other, then you would give it more slack in terms of deciding it actually happened, whereas you bias against the other one because it wasn't as likely, and you want to make sure that the average probability of error is minimized. So you would bias against the less likely one. That makes sense too, doesn't it, statistically? But in most comm systems, that's not the case. In radar systems, they're designed with a different requirement, and this is part of statistical decision theory. Radar systems might be designed to be what's called CFAR, which stands for constant false alarm rate, which means, yes, you want to get the maximum probability of detection, but you want to ensure that the probability of a false alarm, in other words, not a target present, holds to a very small probability, like say 10 to the minus 6th or something, because you don't want to accidentally say, whoops, I think I just saw something. I just saw an ICBM headed my way. I'm going to launch a counterstrike. You don't want to make a mistake like that. You want to be very careful with things like that. That also makes sense, doesn't it?
Right, so you could bias it in that way.
Yeah. So the CFAR idea is something where you just are trying to just say, I'm going to hold fast to the idea. I want to ensure no false alarms. And if it's a simple radar application, the false alarm occurs when noise gets confused with signal. It's just noise present. Don't get excited. Because if you keep lowering your threshold down to the noise floor just to make sure you can detect a really weak signal, now you're going to be increasing the chance you're going to falsely declare noise as being signal. So that's where that idea comes from. You have to be reasonable about things. In digital comms, though, it's different because we can have forward error correction coding and we can figure things out later. In certain radar applications, no, you don't do that. You'd have to get it right early on. Okay, this just revisits the optimum threshold. This is for the equally likely signals. Remember, the bonus problem in the homework is just the analysis to prove what the threshold is for non-equally likely. But for the equally likely case, this is what we're talking about for the two outputs, S01 and S02 at T. And then K optimum is going to land at the middle of the difference between the energies. And if we normalize it by 2, which is so we can work with Z, this decision statistic, then that's the optimum threshold. So it's 1/2 of the difference between the two. So I guess I'll encourage you to try to work that problem. You don't have to. It just involves more math. But that's the bonus problem that's on the homework. Let's see. This one right here. So we're seeing that first term is what we have that's different. That term goes away, though, if P and Q are equal to each other.
Because L on 1 is 0.
Right. Right. Interesting. I worked in optical communications when I first was in industry, and I was always working with thresholds. And I guess PAM system, since we were talking about those before class started, thresholding in there is really important. So that's why I think the problem's going to be interesting. And I think setting a standard, I'm thinking about it now, and I'll probably keep thinking about it. A thing about me and going on walks all the time, I don't purposefully set out to think about a problem. I might leave the house and it's like, I got to figure this out. I'm staring at the computer, I'm getting nowhere. So I start working on that problem in my head while I'm walking, but then pretty soon it's like another problem comes back into my head, one that I thought about earlier, and then it comes, so then I'm thinking about that one for a while. I'm not constantly thinking about work, but I think about it a lot. I might see, my neighborhood is right over here, so the deer are gathered up differently than they were earlier in the season. So we have deer, all the does are together in a clan with their fawns that were born this past summer. They're very cute. I mean, the fawns are still really tiny. They're very afraid of people, but there's wild apples that have grown in somebody's backyard in front of one house over where I live. Put all the apples near the curb so that the deer have now found those apples and they're going crazy over them. But then, so there's I'm giving you an animal history lesson, or not history, but the does are with their fawns, so all the moms are together with their babies. The bucks are roaming pretty much independently, so I run into them too, because they're still part of the whole herd, but they're independent, right? They're very independent, but they're eating in the same apples, but they're generally not, I don't see them at the same time. They might be on a different day or a different time of day. Because everybody's hungry, so they want to eat something. So I'm pretty impressed at how, I know deer like apples. I think they like to eat their food off the tree or the bush, but they have figured out that they're on the ground, they're legit, and they're eating them like crazy. Okay, so now we're going to diverge a little bit and then come back and then diverge a little bit more. Because when I originally rewrote my notes quite a few years ago, I tried to fold in implementation ideas. So this comes from the Rice book, just some block diagrams about how you might implement a system. And I had MATLAB in here, but I decided I'll put Python first and Julia and MATLAB, because that's probably the order of interest right now for me in running a simulation. So baseband modulation can look, in a DSP implementation, can look very much like this for some sort of binary scheme. We have bits coming in, we go through a serial to parallel converter, and the parallel aspect of it doesn't mean as much as it would be in the M-ary schemes, but this picture does have log base 2 of M in it, so the serial to parallel here doesn't really break out into a separate path, but it does also say that encoding would go on in there. So if it was an M-ary scheme and M was, say, 16, then every 4 bits would be grouped together to form a symbol, and then that symbol is what would be emitted into the lookup table, and then the lookup table would produce some amplitude value, let's say, and we'll be getting to that a little bit later in this chapter, but that's what the lookup table would be. It's the mapping between individual bits or bit groupings that corresponds to some lookup table, and then we would eventually drive that waveform into an upsampling operation, and that's what the figures across the top are saying. We have different amplitudes coming out of the lookup table. That's in this area right here. And then we upsample, so we stuff n-1 zeros in between. So this is shown for upsample factor of 4. So there's 3 zeros stuffed in between. And then we'd have an FIR filter of some sort, pulse shaping filter. Right now it'd be a rectangle, but we're going to shift that over to other pulse shapes a little bit later. And then we'd have now it becomes a waveform, and that waveform can be modeled as this superposition of time-shifted pulses weighted by the amplitudes. That would go through a digital analog converter, and now it's an actual continuous time waveform. And now we come around to the receiver, the ADC, it's clocking it, and this simple model of the ADC doesn't show any oversampling, but clearly we'll have to have some oversampling to get some waveform fidelity, because it doesn't know the epoch, doesn't know when to sample exactly, right? We were talking about that before class, but for simplicity right now, it just shows capital T, and then you go into a matched filter, which doesn't really make any sense at one sample per symbol, but I don't know, I guess we could put an oversampling factor in there, so it would be what should I make it be? It should be N.
1 over mt.
Yeah, N over T. So N times the symbol rate, right? So 1 over T is the baud rate or symbol rate, and N times it would bring it back. Match filter then does its thing, and then we have sampling instant based on recovered timing information, and then we make a decision on what was sent. And then we'd go back through the parallel to serial to get, or to decode those symbols back into collections of bits. So in MATLAB, I had a function PT mod, and I need to change this after I read it this morning, since I updated the notes. I need to say in Python I had NRZ bits and other things floating around in the collection. So we'll come back and look at some stuff in the Python Jupyter notebook that was updated. But now we're to the point where we can go on and look at these modulation schemes. So we're going to start with the coherent binary signaling. And those are the 3 types that were defined at the start of this, before we even got into the matched filter. They were amplitude shift keying, phase shift keying, and frequency shift keying. So antipodal baseband waveform, which could also be called NRZ baseband, I guess. NRZ being non-return to 0. And then if it's amplitude shift keying, simple on-off keying, we'd send a carrier waveform when it was a 1, and we'd send nothing when it's a 0, and so on. For phase shift keying, we send a carrier continuously, but we shift the phase of it. At the transitions, we shift from, say, 0 degrees to pi, or in the modulation index, PSK, that's defined in this area of the book and in the notes, there's a phase difference of 2 cosine inverse of m, but typically that phase difference is pi, so it's going from 0, 180, 0, 180, but if it's modulation index m, rather than going all the way down, it will go, it won't go all the way to 0 or 180, it will do something like that, and we're going to see that's going to mean that it's going to average to some other carrier component that's on the cosine. If it's FSK, then it's just shifting frequencies between a high frequency and a low frequency. We're also going to consider along the way some receiver imperfections, and I believe one of the homework problems also has you start looking at imperfections. In particular, the first one you'll look at is timing error in a baseband waveform. What happens if the integrator doesn't start right at the start of the new bit, but starts skewed slightly? And that's gets into what we were talking about before class 2, how that impairs, and so you'll study that. So amplitude shift keying, we assume a carrier, and it's only present when a 1 is sent. So it's sometimes called on-off keying. This is used in some of the simple wireless radios that are used for Internet of Things. It's used fundamentally in optical, infrared controls like for TV and other things. There's actually a standard that controls all of that, but that's an infrared laser diode or infrared LED of some sort. But in the IoT devices, this is the simplest scheme. So this just represents the two types. Correlation coefficient is 0 because you don't have any signal present when you're sending the 0. So we have an orthogonality-like condition. And if we just plug into the results from before, it'll be Q of square root of Z, where Z is the EB over N naught value that we defined at the very beginning of the chapter. This will be 3 dB worse because we already saw that plot, but it's a very simple scheme. It also has one also notable negative, and that is that it requires twice the peak power because the measure there in EB over N naught is the instantaneous value, but in terms of the performance measure, SNR, it'll be average EB over N naught. So that means you have to get an average power or average energy of a bit, you have to have a peak power that's twice because you're sending nothing in between, and that is not necessarily a good thing from an overall efficiency standpoint. The fact that you have to have a device that can put out twice as much power means it has to have more dynamic range.